Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Let's continue with more input generation methods for thermodynamic assessment. These are going to be the contents of today's class. We're going to look at constitutional data, that is phase equilibria data or phase diagram data, how to generate that. We will focus on non-isothermal methods first. First one is cooling curve methods. We have seen this in one of the previous classes where cooling curves are drawn using differential thermal analysis. We'll see about that today. Chemical potential techniques, EMF measurement methods. These were used to generate thermochemical data, but these are quite useful even to measure phase diagram information. And then magnetic susceptibility measurements, resistivity measurements, dialectometry, and especially order disorder transformation, how it can be measured. Dialectometry is quite useful there. We haven't seen about this transformation before, so we'll spend a couple of minutes on that. So this is a second order transformation, so we'll see a distinction between first order and second order transformations as well. Okay, the first one is cooling curve method, non-isothermal in the sense that the temperature is not going to be constant at various temperatures. How the with respect to time, how the temperature changes and any phase transformation happens, that will be noted. And this we have seen in the very first method of phase diagram construction. Just after introduction of physical metallurgy, we have seen this. Take any composition, go to really high temperature, cool it down and see where the changes in the slope happens and mark them as the transformation points, translate them to phase diagram, if you remember that. So this is done through this technique called differential thermal analysis, DTA, and it notes temperature of transformations against time. It's quite useful, and it's quite useful especially to measure solidus and liquidus points. That is DTA. Then the EMF measurement techniques, chemical potential techniques, and with them basically what we are getting is activity of one or all of the components is measured during a cooling or heating cycle, and a series of characteristic breaks define phase boundaries. See, the activity is going to change when the phase boundaries occur. Let's understand that based on this diagram. You see, this is a eutectic diagram. Simple alpha and beta two phases are there. You have seen this kind of diagram. Now, at this temperature T1, let's put a line like this. There's a tie line here. It tells you alpha and beta two phases are in equilibrium with these two compositions, right? Now, if we plot activity of B for this temperature T1 with composition in the x-axis, how is it going to look? You can recall activity of B will be same across the phases. Activity of B will be a single value across the phases alpha and beta, only then they can stay in equilibrium, right? So if that is the case, we are saying from this overall composition to this overall composition, for all these alloys, we are going to have two phases alpha and beta, and the chemical potential of B in alpha and beta is going to be same, right? And then how is the chemical potential of B will be if we cross this line? We are getting into beta single phase. There B is there quite a bit. B is the solvent kind of thing and A is the solute. So B will be pure B at the right extreme. So chemical potential or activity of or activity of B at this right extreme is going to be 1. Activity of B is 1 for pure B, right? And before that, activity of B will keep on decreasing from 1, right? Because A is getting dissolved up to this point. From right to left, if we move, it will come down from 1 to some other fraction, right? And that fraction is going to be the value of chemical activity of B from this point to this point for all these compositions. And then from here onwards, pure A. So activity of B there is 0. So from 0, activity of B is going to increase to some fraction if we come from left to right. Okay. So that's what these lines are going to indicate. This is activity of B going up from 0 to some fraction, and then it is maintained at one value, and then it increases from that fraction to 1. So here it is 1, activity value is 1. Okay, so between 0 and 1 is this y-axis, and this is how you get the activity curve. Now this is a temperature T1. What if we repeat this at different temperatures? You see the tie line here is basically indicating the length of activity being equal, right? And if we come down in temperature somewhere here near this lowest point, we'll see that almost there is no solubility between A and B, and the chemical potential of or activity of elements will be same across this entire composition range almost. So you will see that these points where the break happens is going to shift towards left here, and this is going to shift towards right here. So this is going to become wider as the temperature decreases. So if you mark all the points of break of these activity values, you can trace a solver's line. So in that way you can get phase diagram information from activity measurement at different temperatures. This is how the technique works. And then we have different properties measurement methods. The first one is magnetic susceptibility measurement methods. For determining phase boundaries in magnetic systems, as there is a distinct change in magnetic properties during a phase transition, this method can be used. And here what is happening is alloy is suspended and a pendulum and a magnetic field is applied. The sample is then heated or cooled, so temperature changes. The sample is deflected from its position due to the magnetic transition wherever it happens, at whichever temperature it happens, and then the magnetic field is then altered by changing the applied current to bring back the sample to its original position. So how much is the current applied now is going to be an input to calculate magnetic susceptibility. Okay, so this magnetic susceptibility is then plotted as a function of temperature, and sharp changes will be seen in that, and that delineates a phase boundary. Okay. This is a very simple way to understand how magnetic transformations happen. So in those systems, this technique can be used. Similarly, resistivity, electrical resistivity of an alloy is also measured as a function of temperature. As in the case of magnetic susceptibility, quite distinct changes in resistivity occur during phase changes. So that can be noted and phase diagrams can be plotted. And then this method is quite widely used, dilutometric methods. The expansion or contraction of a sample during transformation is measured. So this is there in many of the transformations. The volume of parent and product will be quite different in many cases. In that case, there is a significant expansion or contraction happens during transformation, and that is measured in dilutometry. Okay. And in fact, dilutometry is used generally to measure thermal expansion coefficient. Okay, so changes in thermal expansion coefficient can also indicate phase transformations, because different phases are going to have different coefficient of thermal expansions. And this particular technique is sensitive to ordered disordered transformations. So this is quite important. This particular kind of transformations are difficult to detect in other techniques. So this technique is quite useful in detecting that. So we haven't seen what is this ordered disordered transformation before in this particular course. We will spend 1 or 2 slides on that. We'll take an example, copper zinc system. What happens in ordered disordered transformation is this: chemical order breaks. Okay, so in copper zinc system, we have a chemically ordered phase, B2 phase, at a low temperature, and it transforms to BCC phase at high temperature. So this is chemically ordered phase, this is disordered phase. You see here in the middle of the phase diagram, there is this B2 phase at low temperature, and after this red line, it becomes BCC. Okay, so B2 becomes BCC. This is ordered to disordered transformation as the temperature goes up. And this is a second order phase transformation. So now we are introducing one more term, second order phase transformation. And this is one of the reasons why it is difficult to detect in other techniques. We will see why and how is it different from first order transformations. Okay. Second order phase transformation. Unlike first order transformations, the change in G and H are continuous at transformation temperature. You see, so the changes in G and H we haven't noticed it in the first order transformation. Let us bring both the kind of transformations and understand these things together. Now, first order and second order are here. In first order, how G, H and Cp looks against temperature and how they look in the second order transformation, it is here. You look at it carefully, this kind of diagrams we have seen, G versus T, a solid curve will be the lowest compared to the liquid curve below the melting point, and beyond that liquid is going to be the lower one. So now if you see here, there is a sharp change in the Gibbs energy here. Similarly, if you see H, this is enthalpy of solid and this is enthalpy of liquid, and there is a distinct change in this enthalpy values right at the melting point or critical temperature here. So there is a significant change in H. In fact, we call this latent heat of fusion. So that is going to be a significant amount of energy, and that is there here. In Cp, if you see, solid Cp is here, liquid Cp is here, and when the transformation happens, the Cp becomes discontinuous. So all these three different values become discontinuous at the transformation temperature. Whereas in the second order transformation, if you see, this is how the Gibbs energy changes look. So they kind of gradually change. So in that way, there is no distinct sharp changes in the Gibbs energy value. So it is continuous with respect to temperature. And H, if you see, H also is continuous with respect to temperature. The gradual changes only are there. And for Cp, we see a distinct change. Okay? So Cp is the only value that is discontinuous in second order transformations. So since it is having this kind of behavior in H value, this is difficult to catch in the calorimetric experiments. So the dilatometry on the other hand can be quite useful if the volume changes between this order disorder is significant. We are going to catch that in dilatometry. Okay, thank you. With that, we'll stop today's class. See you in the next class.